supervised classification. What does this mean? Well, we put more input up front. We supervise the classification. We want to tell it where to put the seed to begin with, so to speak. It's not quite the same process. It's not quite the seed as such. But if we look in this image here, we say, well, that's a field there. Whenever you find something that looks like that, well, that's a field. That's what we're telling the computer. Now that's a wet field. So if you see anything that looks like that, it's a wet field. You're informing, you're supervising, you're helping it along the way. And then once we do the classification, we can get, well, how did that? Well, we'll come back to that later. Surely that should all be one class. I mean, I told it that that was the field, a wet field. What's going on there? Nothing is ever perfect. So if we look into the image and identify these areas. And what we're looking for are homogeneous areas. Yeah, here we have a problem already. Because what we want is an area that represents our object of interest or class of interest, our information class. And it needs to be spectrally homogeneous. We don't want too much mess in there. We want it to be a clean signal. And a lot of surfaces are very difficult to get a clean signal from. When we look at this, we've got different shades of green and darkness in here. It's a very varied signal. It's homogeneous in the sense that that's all woodland. That's all deciduous woodland, and that's all coniferous woodland at this time of year. But we can see that it doesn't look spectrally homogeneous. But that's just something we're going to have to deal with. It will cause problems. But these, we define these areas, these so-called training areas, because we're training the computer. This is what a field looks like. This is what a body of water looks like, a river. And we have to have the same kind of thought that we had in the unsupervised, in that there's variation. We might have a class that is coniferous woodland in shade. Or we can say this is a subclass, this is field, but it's a wet field. So this is how we can then build up our information class library, so to speak. By defining these areas, we then tell the computer this is what to look for this kind of signal. The thing is, we have to really kind of know what we're doing. We shouldn't get confused by variations in the image. We can't be complete novices at this. It does require some other information. We need to have some expertise. What is it that we see on the ground here? This is why doing our courses in earth science and physical geography, they're important for us, even in remote sensing GIS, regardless of how you've come into this course. And having an understanding of the physical world out there, the processes that occur and what things may look like, just observing them and seeing what they actually look like helps, is kind of necessary, because we need to know that this is a field for particular reasons. We need to know that this is essentially the same thing. We just know that there can be this sort of variation in it. Sounds obvious, but unless we've trained ourselves and built up these skills, it can be really quite difficult. So we need to have this information in our heads in order to inform the computer. So when we look at this series of images, series of training areas, we then pick out all of the pixels, plot them into band space again, as we did before, to create spectral classes. So we go from our information class to a spectral class, and then we will go back again. So we have to create a spectral class from these training areas. Now, one thing to avoid, and this is kind of separate to the lecture, although it is important, certain programs will allow you to create multiple training areas for a single class, which is going to be problematic because, as the previous slide emphasized, we want homogeneous areas, and they're difficult enough to find as it is. And if you can combine multiple polygons into one class before you even do the analysis, before you've created the spectral class, you're not likely to get very clean signals. Even here, it's not very easy. I've just made this stuff up, but it's a fairly accurate representation of what the reality is. Getting a homogeneous signal from an image can be very difficult. So Stay in control of what the program is doing. Don't let it run away from you. This is not necessarily a problem in QGIS or ArcGIS. Both of them manage this process quite well. Other programs sometimes, as I said, they can allow you to use multiple polygons as one training area. You don't have to, but they will allow it, and that can be a problem. So once we've done this, we've informed the computer that this collection of pixels in the image here, that represents a field or a forest of one sort. It still needs to be able to analyze this. At the moment, it's still, for the computer, just some numbers. So we need to be able to somehow help it on the way to define where is a group. You need to be able to see these groupings. It can't. We can, again, fantastic brains, blah, blah, blah. We can see all these groups, the computer can't. Not without doing some sort of analysis, numerical analysis of what's going on. So we're going to look at some of these different methods now. And we have two main categories. Always categorize things into, that's just what we do. So we have something called non-parametric and parametric. Non-parametric may sound, non-parametric and parametric. If you're not familiar with statistics, that can be a little confusing. Parametric just basically means mean, standard deviation, all of those basic statistical descriptors. Non-parametric means not that. So we'll go with those first of all. The first method is the so-called parallelepiped. It's a good word, parallelepiped, otherwise known as box. Let's just call it box because frankly it's a silly word, parallelepiped. It's the word, you'll see it down there on paper quite a lot. Box. And what we're doing is we're saying we'll just draw a box around those pixels. We've identified these pixels. So we can sort of say this is like a training area. There's not exactly, the training area was a thing in the image, in the actual aerial photograph. We drew a polygon around it, and they said anything that's in here, those pixels look like a field or whichever it was. And then we take those pixels, plot them into band space, and then we kind of do a similar thing. We say, well, all of those pixels, anything that's within that box, that is also that's a field. So we get this, and that's, it's very simple, very quick. This is non-parametric. There's not really any mean or standard deviation or anything like that here. But we have problems here because we have pixels like, say, this one that doesn't fit in a box anywhere. So what class does that belong to? That becomes unclassed. Well, that's okay. So that's easy enough to handle. Unclassed, in a sense, it doesn't belong to a particular class, unclassed. But what about this one down here that belongs to two classes? Because we've drawn these boxes around here in this fashion, and they cover in every pixel that belongs to a particular class, and just draw a simple box. This can happen. We can get this overlap, and there's no easy way out of it without actually starting to go parametric, as in try and find some statistical mean point, or maybe we can do some geometric analysis here. It starts getting quite complicated though. And we wonder if this is actually as useful as we'd hoped. I mean, the big advantage with this is it's very quick. Just draw boxes around everything. The analysis is done super fast. Great. But maybe this is not the best way of doing things always. So we can do something, say, minimum distance. We start looking at statistical assessments of the data. So, well, we again, like we had before with the seeds, we just create the average point, for example, and use that as our way of identifying what class a new pixel should belong to. So these were pixels derived from our training areas. We calculated a mean for those pixels. And then when we get the new pixels in, the ones from outside of the training areas, the image as a whole, we want to reclass everything. We forget what class all of these pixels actually belong to. We've now created our seeds, our class centers, and then do the analysis again. Which pixel are you closest to? Sorry, which class center are you closest to? And it's fairly obvious that they're all going to end up, these ones are all going to end up in belonging to that class because they created it. It feels kind of logical, not always. And then we have these ones will end up there because that's the closest pixel. And then we come to these two, and that we can put that one, the closest one is there, so that gets assigned to that because it's closest. And that one, this gets confusing because which class would we rather that one belong to? Because it's kind of, in a way, it kind of looks to our eyes as if that actually belongs more to the green to the pink. There's a kind of linearity in this distribution of the pink ones here. It doesn't, and that one seems more spread out, and it should incorporate that one more. Feels like it, but when we just do this minimum distance, now that one works up there, but that one, that just became pink. That was, it's closest to that one. Minimum distance, kind of simple, not always right. So we can try and make things a little more complicated. We can do something called maximum likelihood, for example. Maximum likelihood is a concept that's used in lots of different places. This is massively simplified, and the visualization is entirely great, but we'll get the gist of things. So what maximum likelihood does, in this case, we're expecting a normal distribution of the pixels. We've said these pixels are a particular class, and I'll find the mean of those and the standard deviation in multi-dimensional space. I'm not showing this in multi-dimensional space. In fact, this visualization is rather one-dimensional. But anyway, we find this the best fitting mean and standard deviation, the best descriptor according to a normal distribution. We use this as the normal distribution. We find a mean and a standard deviation that creates the that fits the data best. That's the maximum likelihood for that. So we test different values of the mean and the standard deviation to best explain the maximum likelihood that is the correct descriptor of this group of pixels, and that's the best descriptor of that group of pixels. And then once we've got that, we use the similar concept to then say, well, which pixel do I most likely belong to? Which group of pixels do I most likely belong to when we look at that? So let's look at that pixel there and say, well, kind of in line with both the pink and the purple. I think we can see where this one's going. I belong, when we analyze it along this line here, we can see that, well, I'm that much in the purple group. And when we look down there, there's not really very much. There's a tiny little fraction of me that sort of happens to lie on that part of that line. That's really not much. So most likely I belong to that one. So it's the maximum likelihood that I'm in that group there. And then when we look at this pixel here, we had hoped that this was going to resolve the situation. We got that there. There's that much greenness to me, but there's that much pinkness to me. Well, we end up as a pink one again there. This is a problem with perhaps the visualization, but there's also a problem that this exists. It's very difficult to get a correct solution. This problem would have gone away if I'd actually made a proper two-dimensional analysis of this, and we could have got this kind of the slope of these group of pixels in there and rotated all these things around. That the visualization might have helped a bit better then, but we didn't have that. And we can see the weakness, but this illustrates the weakness of this method as well. It doesn't always work. It's a good, strong method, and we've seen it. It can be an improvement on previous methods, but nothing is ever perfect. We always have to accept that the classification will not be able to capture all details, all nuances of the variation in the data set. That's just the way it is.